back soon. Okay, perfect. Yes. You are muted. Maybe you need to unmute yourself.
Yes. Hi. Yeah, I'm trying to. Can you guys see my screen?
Yes. Yes. But you need to. Oh yeah, that's good. Perfect.
Okay. So there'll also be. Thanks for the kind introduction. It's a great pleasure to be here. This time around, I'm going to do something different, and rather than talking about my own research, I'll kind of lay out a research agenda focusing on some of the collaborators' works, and then postulate a future problem sort of as a position. I will present a video inside the presentation, and I'm curious to know if the screen sharing that I'm doing will have the video enabled. So give me 1 second, I'll just double check if that works. So if I
you
do
need to reshare the screen again, I think.
It says that okay, so share sound. Okay, that's what I need. Okay. Can you share can you see it?
It's yeah, now we see it, yes.
Okay, cool. All right. So before I get deep into my talk, I'd like to read out something that Rich Caruana, who is hopefully here today, right now, mentioned almost 30 years ago about multitask learning in general. That it may be easier to learn several hard tasks at one time than learn each of these tasks independently. In effect, the information provided by training signal for each task serves as a domain-specific inductive bias for other tasks. So in other words, for many domains, acquiring inductive bias by collecting additional teaching signal may be more practical than the traditional approach of codifying domain-specific biases from acquired from human experience. So I think this is pretty profound, given that this was thought of, and postulated 30 years ago. So this is a multitask learning workshop, and we've been talking about this for quite a while. So I just want to summarize a little bit of why it's important to do multitask learning. First of all, it's biologically motivated. So when we learn to do things, we don't learn how to do them in isolation. When my kids learn to play tennis, we don't teach them to first run, then jump, then to throw, then to recognize objects, then to swing the racket. They kind of learn everything jointly. Secondly, a generalization helps here quite a bit, right? Running in tennis isn't quite the same as running in soccer, but when kids learn how to play tennis and learn to run, when they switch to another sport, it becomes quite a bit easier.
Just one, what checking is it in your presentation mode, or we see it's probably.
Oh, you're saying okay? Let me switch.
Yeah.
How about now?
Oh, no, it's good. Yes. Initially cool. I thought this actually intentionally it was but yeah.
No. Okay, cool.
Ahead, yeah.
All right, great.
No, it looks good. Yes.
Cool. All right, cool. And lastly is the regularization component. And here is the big point is on the inductive bias. You want to learn multiple tasks at the same time because each task actually helps to learn the other one. A little bit more on the inductive bias. So inductive bias is anything that causes an inductive learner to prefer some hypothesis or solution over the other, right? In 1980, Mitchell has postulated that inductive free learning is essentially impossible, and much of the power of inductive learning follows from the inductive bias. So multitask learning is predicated on the notion that tasks can serve as mutual cross-source inductive biases for each other. And of course, a lot of, for example, benefits and wins in transformers that we're seeing today, the pairwise interactions that transformers exhibit is a form of an inductive bias. And this is just one of the latest examples where inductive bias is very powerful. All right, so today what I want to talk about is multimodal multiple tasks. So rather than just solving multiple tasks in a single architecture or in a single model, or even considering multimodal tasks in a single model in isolation, what if we want to solve multiple tasks that are only solvable by considering multiple modalities? So to sort of motivate the entire presentation, I want to show a quick video, and please stop me if you can't hear the audio.
We don't hear the audio. Yes. Andrew, we don't hear the audio of your video.
You still can't hear it?
We don't hear. I mean, we can hear you, but not in like the voice from.
Okay. Let me fix that a little bit. 1 second.
Yeah. No problem.
How's that?
Yeah, still not. You see like a kind of icon there. Seems that the audio is muted.
Hey, sorry
Now
about
it's
that.
good. Yeah.
That's actually one of the problems that we're trying to help fix. What I was saying was Headroom is a full meeting platform. And I say meeting platform because we do more than just screen-to-screen faces. Not only do we have tools to help make meetings more productive, inclusive, organized, and on track, you can save pretty much everything that happens in a meeting to revisit and search through later. Now, we all know the mute button is a pretty great thing till it's not. That's one of the original reasons why we have built-in gesture recognition. You can give a thumbs up or a thumbs down for a quick vote, or you can raise your hand to get someone's attention. Even when they're busy in a brainstorm and can't see you on your screen, you can get a hold of them. Now, brainstorms are actually a great example of how you can use our first facilitator tool. As a meeting facilitator, it can be super helpful to know how well balanced a conversation is. That's where word share comes in. We can give you real-time feedback and nudges when someone is hogging the conversation or when someone's been left out. Here's what it would look like if other people were added to the meeting. As a meeting facilitator or presenter, sometimes it can be hard to read the room, especially over video chat. And we can help with that by sharing the group energy of the room. When folks are excited and engaged with the product, the energy is going to go up. And when folks are not, and the energy is low, it can let you know maybe it's time to take a break, stretch, or regroup. Really, it gives you the room to make the room, to get a feel for the room when you can't exactly be in the room. And I know that you got all of that, but just in case you didn't, we got you. We have a real-time transcript, so if you miss something or even miss the last few minutes, you can scroll back and take a look at everything that's been said in the meeting. Now, let's say someone made a great point and you'd like to elaborate on that. You can click on a piece of the transcript and it'll add it to the notes. Oh, yeah, we've got notes. You can take notes together as a team right in the meeting. It comes with everything you'd expect. Everyone can edit at the same time, comment, and assign action items for folks to follow up on later. And you know what the best part is about being a full platform? All of this is saved for later. It's automatically shared with everyone in the meeting. You got it. If you choose, a video replay of the whole meeting is saved for you to watch back and even interact directly with. It's more than just a screen recording. You can watch at your own pace, you can change views and arrangements through playback, and you can navigate through the video using the transcript or notes to get highlights of the meeting. Or you can share highlights with stakeholders and other team members to let them know what happened in a meeting. Now, if you're looking for a higher level view to share, you can revisit the meeting page and see a summary of the notes, word share, action items, and more. But what if you're looking for a specific moment in the meeting, or any meeting for that matter? All you have to do is remember something small from the meeting and hop back to the homepage. Above the list of your past and future meetings, you can search across all your meetings by the vague things you remember, but you can't quite put your finger on. With one keyword or phrase, you can search title and description, you can search notes, transcripts, guests, energy. Basically anything that's saved is searchable. It's pretty cool, right? You know, we're just getting started. There's plenty more to come. No matter what, if you're discussing, presenting, or collaborating, we're going to give you the headroom to focus on what matters most to you.
Okay, so in order to solve all of these tasks and actually make the sort of next generation video conferencing possible that Headroom is working on, we really have to work out a ton of different things from both the vision and language and audio perspective. So here you're seeing some of the tasks that we're solving at Headroom today, from face recognition to 3D reconstruction, from hand tracking to effective computing. At the same time, we're tackling natural language understanding for transcript diarization and utterance sentiment. Now, as I pointed out earlier, the outputs that we're seeking for effective understanding of video conferencing are these boxes that are captured in the red at the bottom. So these are like the nonverbal appeal. When somebody is giving a thumbs up, it could be possible that they're, you know, just scratching their face with a finger and not really responding to a particular question. If someone's asking, how are you doing? And somebody gives a thumbs up, that is a direct answer to a question. And that should be considered a multimodal gesture recognition versus just understanding that someone's holding their thumb up, right? There's engagement analysis. Are people actively involved in a conversation? Are they smiling in context of what's being said and the reactions to something that's going on in the meeting, or people are just smiling for a different purpose? So in order to understand all of these different components, what we really need to start looking at as a sort of research community, both in academia and industry, is to start learning the interactions between the different modalities and how they interact with each other to produce results for these multimodal, multitask learning approaches. Given that this is a vision conference, I'll preface the discussion by saying that as a vision community, we have started to really understand how these multi-vision tasks relate to each other. Chelsea mentioned some of the work in her talk that discusses how different problems in vision relate to one another. There's been a work in CVPR from a few years ago that discusses how different tasks relate to one another. However, when it comes to multimodal tasks, there's really very little work done in that domain. And I think that's something that we need to improve upon. So in multimodal approaches, the relationships between tasks are still in their infancy, right? Where it essentially spans problems like visual question answering. There's a textual question presented in some image or a video, whether we want to find out if somebody is wearing glasses or not, and their image is presented. So essentially the object detector is prefaced with a set of categories that can be extracted from the text associated with the image. The next level is you can have a textual output that's correlated with the text. In this example, there's an image of a female who is making a comment about a particular person, and they're saying, all I can say is he's a pretty average guy. And then there's a facial expression. In using effective computing, we are trying to identify if the person is sort of happy, sad, where the valence and arousal correspond to the textual description or not. So these relationships are still very, very, very vague. Now, if we start with an example where there's these two men are sitting and they are presumably crying, and one hypothesis would be whether one person says he was such a great guy, and this would be sort of the output that they're at a funeral, or the alternative could be that the person two says, no, they look so great together, and it turns out that they're really sitting at a chapel, and there's a wedding happening. So the understanding of text to vision can really lead to very significant different outputs, and that's something that we try to capture. So the problem statement is referring to the fact that theories of language origin actually identify the combination of language and nonverbal behaviors, which are vision and audio, as the prime form of communication utilized by humans throughout evolution. And this was sort of postulated over 150 years ago. So the goal here is try to consider human interactions and communication in particular as this multimodal, multitask problem, where without seeing, just hearing, or just reading isn't really sufficient to disambiguate the task in itself. So here we have 4 people present in a conversation. Each is able to generate utterances, which are driven by text, audio, and visual appearance. And the goal is to measure the sentiment and the emotion of such utterance. And utterances are defined by vision, audio, and text. So the recipe that we would like to follow is to be able to capture the state of the speakers and listeners. Then we want to capture the context of the conversation. And then finally, sort of in an encoder-decoder language, we want to be able to capture the joint emotion and sentiment of the utterance given the existing observations. Now, in order to do this, obviously, most of the work that we do these days is very data-driven. And the best data set today comes from CMU, and it's called MOSE, where it's the largest sort of this multimodal data set for multitask learning, and consists of audio, over 3,000 videos, and over 20,000 sentences that comprise the utterances. And the task here is to learn both the sentiment of the utterance on the left, negative, weakly negative, neutral, weakly positive, and positive, and then capture the 6 sort of most standard emotions: happiness, sadness, anger, disgust, surprise, and fear. And that's the goal. The visual features are the standard things that we're all used to: bounding boxes of faces, landmarks, shape parameters, head pose, eye tracking, face embeddings, and so forth. The audio features include the 12 mil frequencies, spectral coefficients, pitch, voice, and so forth. And when it comes to text, all videos have transcription, so each of the transcribed texts are embedded using the glove word embedding, but it can be done with anything that represents a nice language model, whether it's a BERT or GPT. Now, in order to go back to this idea that we want to learn relationships between tasks, initially, we want to learn the relationships between modalities. So initially, we can start by unimodal sort of interactions. And in order to understand the multimodal interactions, we must consider all possible combinations. So here there's this dynamic fusion graph introduced by Zada et al. In 2018, which implicitly models the n-modal interactions. It does so with efficient number of parameters and can dynamically alter the structure of the chosen graph based on training data and the examples. So now when you take this multimodal representation of interactions between modalities and add it to the actual learning framework, you have this paradigm that allows you to do learning and update the graph in real time. So to test the performance of this dynamic fusion graph, There's a recurrent neural network with three main components. First is this, on the bottom is the system of LSTMs, which is a set of parallel recurrent models where each one of them models a single modality, vision, language, or audio. Then there's the dynamic fusion graph that performs multimodal fusion by assigning coefficients to highlight cross-modal dynamics. And finally, there's this multimodal state memory that complements that stores the output of the multimodal fusion, and then further allows these the previous state to impact the future predictions. And then we just iterate over this process and are able to learn the interactions of multimodal effects. So first question in this approach we want to answer is, does multitask approach help? And here in purple, you see the single task learning, and then in the striped versions of the multitask learning. And we evaluate across a number of metrics for both sentiment and emotion. And as expected in both cases, we can see that through the regularization of this inductive bias, both emotion and sentiment are improved with the multitask approaches. Next question, naturally, we want to ask, does the multimodality help? And here we compare this Graph-MFN approach to singular models in language, vision, and audio. And we're able to see that both the sentiment and emotional performances, with the exception of a couple of categories, we do get an increased performance by applying multiple modalities because they help disambiguate the problem. So given that we've been able to combine multiple modalities into a recurrent architecture and have shown that it improves the performance, the next question is, how can we do better? And in order to better, it's interesting to consider the context of the conversation and basically to come up with a prior on the behavior of the participants or the agents in this case, and to capture the context of prior expressions. So to do that, let's consider a similar model to the previous one, where here, instead of simply looking at the output of learned multimodal interactions, we consider the contextual intermodal attention. So here we have 3 bidirectional GRUs for capturing the context information, 1 for each modality. And consequently, we introduce a pairwise intermodal attention mechanism where vision and text and audio and vision are learned in joint association between multiple modalities and utterances. The objective is to optimize on the contributing features by putting more attention to the respective utterance in the neighbor and the neighboring ones. So motivated by the residual connections of ResNets, the outputs of pairwise attention along with representation of individual modalities are concatenated. And finally, the resultant concatenated representations are shared across 2 branches of the proposed network for the 2 tasks of sentiment and classification. Again, if we look at the performance, we're seeing that if you look at the text plus audio plus video columns, you're seeing that the performance improves both for sentiment and emotion. The next bit that is interesting to consider is how can we really improve the performance by learning the outputs of the model jointly for multiple tasks. So not only do we want to combine the multiple modalities, but we also want to combine the multitask approach for the learning of the predictions for multiple tasks. So here there's the proposed model attempts to model 3 of the sort of modalities that we're discussing, and here we're just looking at one of them at a time. So the three the components here are this the S GRU, which models the state of the particular speaker. Then there's the context GRU that keeps track of the context of the conversation, and there's this emotion GRU that is used to keep track of the emotional and the sentiment state of the particular participant, and is really acting as a decoder of the state of the presenter. There's also a pairwise attention mechanism that I'll touch upon in a couple of slides. So let's look at these components individually. First is the context GRU, and there's one for each modality, and it aims to capture the context of the conversation by jointly embedding the utterance representation of that modality at time t, as you can see in the diagram, and the previous time steps for the speaker that we're interested in. This accounts for the inter-speaker and inter-utterance dependency to produce an effective context representation. And the current utterance T for the audio and the visual and textual representation changes the state of the speaker from ST to ST+1 for the respective modalities. Next is the state. We want to be able to keep track of the participant's state involved in the conversation. The state associated with the participant outputs a fixed vector, which serves as an encoding that represents the state, and is used further by the emotion and sentiment prediction directly. All states are initialized from the initial inputs of the model, given the representations that we had discussed earlier. Here, what's important to discuss also is the sort of very simple attention mechanism, where we just do a softmax over all contexts from sort of time 1 until time t, and then the attention representation is just a concatenation of the weighted representations. The state GRU then in turn takes the previous state S sub t and combines it with a attention representations of context from the previous state. Having described this, now let's move on to the emotion GRU, which really serves as the decoder for the encoding produced by the state GRU, producing a vector that can be used both for sentiment and emotion prediction. The emotion state here uses the previous timestamp emotion, and the encoding provided by the state GRU to produce a representation, which is further sort of combined across multiple modalities with an attention mechanism to produce a relevant output. So at a timestamp t+1, the emotion the emotion vectors are updated as illustrated here. The pairwise attention mechanism is very similar to the previous work that we had described, where there's pairwise attention blocks between text and audio, text, audio and video, and so on. And then using the skip connections, we're able to do a three-way combination to come up with a combination of the multimodal representations to be fed into the final prediction layer. Okay, so when we combine all these components together, we can start looking at an example where you have multiple participants in a conversation. And what we can see here is that as the sort of context and state and emotion for the individual participants are present, now we're able to start reasoning about on a multi-person interaction, where one person would, ask a question, how are you doing today? Another person would, give a thumbs up or nod their head. And these actions are now able to be reconciled in context of the multiple conversations or multiple interactions, right? So that's sort of the state of the art of modeling, explicit modeling of multimodal, multitask learning for this paradigm. And recently, there have been ideas around extension of this. And the first one that comes to mind is this idea of transformers versus GRUs, and why is it possible to use transformers to extend this beyond the existing state of the art? And the benefits of transformers, of course, are the fact that they're able to avoid recursion in order to allow parallel computation. So that reduces the training time greatly, because rather than looking at sort of directed sequences, we're able to learn directly from sequences in their entirety at the same time, right? Finally, the idea of being able to present everything in a single model without having to very carefully craft the design of an architecture is also a very big benefit. And of course, there's no forgetting, because transformers are able to sort of capture arbitrarily large sequences with long memory. So here's an example of how we can apply a transformer to this particular task. On the left, you're seeing a monomodal transformer. The blocks here are fairly well known. There's a multi-head self-attention to the input, then there's some normalization, multi-layer, fully connected layer, and then another normalization. When we extend it to multiple modalities, we can concatenate these single modality blocks together and proceed training them jointly, and then combine them in a uniform multimodal decoder. So if we look at the performance of these kinds of approaches, we're seeing that in some cases the transformers outperform multimodal transformers outperform the existing state of the art, and in some cases they are comparable, but there's a lot more work to be done. Ideally, when we think about transformers, we'd like to think of a task where you have essentially a single transformer that takes everything in and then outputs all the desired tasks as you want. And there's a recent work from a few months ago from Facebook where the goal is to answer a bunch of different questions around object detection, visual question answering, language, and so forth, where variable inputs are provided, whether they're images, questions, general paragraphs, and so on. And for that, the authors propose an architecture that considers two modalities, image and text, where both are pre-trained with their respective large data sets to produce text embeddings for text, and then use some very large convnet around ImageNet or COCO in this particular case to generate representations for the transformer input. Then the two representations are elegantly just concatenated, and then with a task index, a single multimodal decoder is able to attend to a number of outputs that are task specific given the task index. So here we're able to see that the performance of this model is also comparable and to the previous transformer models. But what the authors were able to show is that it is indeed possible to learn multimodal tasks in a single multitask representation, which is our initial goal in the first place. So now if we go back to the problem that we started with, where in human interactions, we'd like to capture these multimodal nuances to understand the nonverbal appeal, the engagement analysis, key phrase identification, topic discovery, and many others. We have to solve all these tasks. The proposal that I have here is to basically adapt some of the previously discussed approaches and in the following way. So we have a single transformer model where there are three inputs. The images correlated to a given utterance. There's text associated to the utterance itself, and then there's the audio. They're all pre-trained with respective embeddings. In the case of vision, on the left, you're seeing these different tasks that we'd like to pre-train the model with, so that the transformer can self-attend to these feature maps during the encoding stage. Then, of course, they all get concatenated into a single representation, and with the multimodal single decoder, we're able to answer all of the required questions that we're interested. And this is essentially how a lot of the things that you saw in the Headroom video, a lot of these tasks are being tackled today. So in summary, I'd like to point out that, multitask learning works because of regularization. It generalizes. Clearly, context matters. And that's why it's such an attractive approach. But here, the take-home message I'd like to formulate is that multimodality is equally, if not more important, as multitasking, because without joint representations, the results are too ambiguous. And when you see somebody smile, it's not obvious that they're happy because someone tell a joke or because they're lying, and that's their sort of coping mechanism. But multiple modalities help disambiguate this and solve the problem directly. So I think I'll stop at this point, and I'll take any questions if there are any.
Okay, yes, thank you for the excellent talk. So yeah, are there any questions to Andrew for his talk about his work? So you mentioned maybe transformer. I mean, here it's one of the, right now it's very trendy topic. So maybe can you share with us more like insight? Is it also possible, or like how easy it is to apply transformer to more general multitask learning? Let's say you have multiple typical multitasks, and normally we actually still formulate them in convolutional neural networks. But then, do you see that this is also promising, or?
So the convoluts are necessary. So we think of a transformer as a sequence-to-sequence model, right? Mm-hmm. So they became very popular in language because you can represent a sentence as a sequence of inputs. For example, for machine translation, if you want to go from French to English, there's a sequence of words in one domain and you want to translate it to the other. And that's where transforms shine, because there's positional encoding, so the order of things are preserved, and you can consider arbitrarily large sequences that you want to operate on. So if in GRUs or LSTMs, there's these problems with vanishing gradients, so that very large sequences are hard to handle, because by the time you analyze token K, token 1 becomes less relevant just because the gradients don't reach it anymore. So transformers address these problems very well. So the next question that we have to ask ourselves is, how can we represent vision tasks in the form of sequences? So if we take object detection, for example, does it make sense to take an image and break it up into patches? And patch-based methods are sort of the classical way of doing computer vision from the past, with fully connected, fully convolutional models. We kind of stepped away from this, but now we see in sort of a return to this patch-based approach, because it allows us to take any input, whether it's images or video, and we represent them as patches or elements in a sequence. Then we can apply them to transformer models.
Yeah. In that sense, that you agree that this transformer could actually unify the use of multimodality, different type of data, could be actually somehow it's a better way to unify this learning.
Absolutely, and that's exactly why I brought this up, because the existing approaches that are kind of that hold the state-of-the-art results and are common to multimodal multitask learning the architectures are still very hand-tuned. It still requires immense domain expertise, like I was showing with this the dynamic fusion graph. You still have to be very careful as to how you combine all the modalities together, how weighted they are, and so forth. In the transformer case, you essentially don't think about that anymore, allowing the transformer architecture to just learn the dependencies by itself.
Okay, yeah, that's great. Okay, then we can, in the interest of time, we can move on to the panel discussion. Yeah, thanks a lot, Andrew, for your excellent talk. So, we have